My name is Lara Newsom. The talk that you are attending right now is called Signals Through Time and JavaScript. I work at Cisco. I'm a software engineering technical lead. I'm a co-host on the Angular Plus show, an Angular GDE, an NX champion, and I have Angular courses on Pluralsight. I also just released a course on Angular signals on LinkedIn Learning, so those are out. I have a ton of abandoned code on my GitHub repository that you can go judge me for. You can reach me on LinkedIn or Blue Sky if you'd like to reach out. So the reason I wrote this talk is that in version 16 of Angular, which was released in May of 2023, they introduced signals to Angular. In Angular, all of us were like, what are those? We had no idea. It wasn't something that we were familiar with. But I started looking around in other JavaScript frameworks and just the ecosystem in general, and there are signals-like integrations all over JavaScript. And then there's also a TC39 proposal to add signals to JavaScript. And so I thought it was important to have this talk to kind of understand what signals are, how they're used, what problems they solved, and why we might want to integrate them into JavaScript itself. So the takeaways I hope you get from this talk are what signals are, why we use signals, and why we might want to standardize signals in JavaScript. So before we go too much into what they are and all that, where did they come from? So just like Doctor Who, concepts like signals have been around since the 1960s. So early computers were used mostly to perform calculations and store data. And in fact, early spreadsheets were invented in the 1960s. Now, it required programmers to make changes to the spreadsheets. So if somebody says, okay, hey, this calculation is wrong, we need to update it, an actual programmer had to make those changes, and then they'd have to refresh the spreadsheet multiple times to get the data to stabilize. Enter René Pardo and Remy Landau. They invented forward-referencing natural order calculations in 1969. So basically, if you've used something like Excel, you've used something like signals. So it allowed spreadsheets to perform the operations in the right order to get the same results every time without having to do multiple refreshes. So meanwhile, on the World Wide Web, so some of you are old enough that you're hearing that dial-up sound in your head right now. The early internet was mostly just read-only, and user interactions caused postbacks. And then the server is the one that reconciled the state. It would just send the whole page in, so we'd see these full postbacks. So then on repaint, the entire DOM would be destroyed, so you'd request the new page, it'd come in, the whole DOM would get destroyed and repaint the whole screen. So you get that full page postback. The data was consistent, but the users had to wait, right? And people are not patient. Nobody likes waiting. So when we got like HTML5 and CSS3 and JavaScript, we got better website reactivity and user interactions. So JavaScript improved reactivity by allowing the browser to update the DOM directly. And it allowed dynamic user interactions. Like we used to do rollovers with JavaScript. Like that was pretty amazing to be able to do that. And we could help improve the perceived performance of our websites. Even if they were still a little bit slow, people could see that something was happening, so it made them a little more patient. We had jQuery, like that felt like the bomb, right? Like, oh my gosh, there's like a whole component library. I no longer have to figure out how to do accordions, right? I kind of thought that was peak, but and then we had Ajax, so you could just do partial page updates. Like that was a huge deal. But as JavaScript started to perform more asynchronous tasks and trying to manage different parts of the DOM, keeping the state accurate between the DOM became difficult. So we had issues managing our async data changes. We had one-to-many dependencies between data sources and DOM elements. Changes to data may initiate changes to any number of dependencies. So updating something, adding something to your cart might also increment a component over here. It might change something over here, right? And so we needed a way to notify all the dependencies of the changes at the same time and get the DOM to refresh at the same time. These are really some of the problems that are defined in the observer pattern, right? So this is how space was created for modern JavaScript frameworks. So the rest of this talk, I stole heavily from Ryan Carniato from this article, The Evolution of Signals in JavaScript. This is a really great read if you want to read the writings of Ryan on this topic. There's a link to that article in the slides here. So the JavaScript frameworks had responsibilities, right? We needed to bind data to the DOM, handle browser events, update the DOM, and we also needed an improved developer experience, because anything that you can do with a JavaScript framework, you can do with JavaScript, right? It's just a real pain in the butt. So our early declarative JavaScript frameworks, we got Knockout, Backbone, and Angular all in 2010, pretty quick succession, and they all handled things a little bit differently. Angular does top-down dirty checking, Backbone did model-driven re-renders, but Knockout did fine-grained DOM updates. So Knockout was sort of where, when you talk with Ryan, Knockout was one of the first places where he started really, where we started to see this fine-grained reactivity that was built on something like signals. So what is fine-grained reactivity? So fine-grained reactivity automatically updates the UI, but it targets the updates to DOM nodes with changes instead of re-rendering the entire DOM. So this also can help avoid unneeded re-renders of unaffected nodes. So one of the performance issues we can run into with React or Angular is that the entire DOM refreshes, or you have to run the change detection on the whole thing to see what changed. Whereas fine-grained reactivity, they know what changed. So coarse-grained reactivity, so this would be out of the box what React or Angular does. Something happens, the entire system runs to see if anything changed, and then it changes the affected nodes, right? In fine-grained reactivity, something happens, and only the affected nodes do work, right? So we want to get to where we're only doing the work on the affected nodes instead of running the whole system again. So Knockout didn't quite get it right. They still required multiple cycles to sort of stabilize the correct state of the application. And that, if you remember, was the issue with early electronic spreadsheets. That's why these guys invented forward referencing natural order calculation. So then we get the idea of push-pull reactivity. So the idea with push-pull reactivity is that change notifications are pushed out, and the execution of the derived state is deferred to where it's read. So if you never read the state, it never executes. So this causes the system to run only once and in the correct order. So MobX implemented consistent glitch-free propagation with a push-pull hybrid model of reactivity. Again, this is an article that kind of goes into, it literally says it's an in-depth explanation of MobX, so if you'd like to read about that. Vue uses fine-grained reactivity from the start, and it also took it one step further by scheduling when updates were processed. So Vue uses something like signals under the hood, but it also handles actually scheduling the updates. So fine-grained reactivity handles synchronization defined in the observer pattern, but it actually doesn't address memory leaks that can come from long-lived subscriptions or notifications. So Svelte comes into the mix. Svelte 3 uses the compiler to allow analysis of synchronized systems. So Svelte actually knows what changed and where. Svelte also has a signals-like concept. And then there was SJS. So you might say, well, what is SJS? Because it's a very small library that not a lot of people use, but SJS implemented several key features of modern signals. They implemented automatic dependency graph under the hood, so the signal knows who its consumers are. It implemented a synchronous execution engine, and it took reactive ownership and automatic cleanup, so it handled the cleanup issue for us. So SJS signals, the dependency graph created relationships between data signals and the computations that were derived from them. Right, so it understood those relationships of the data. Any changes to a signal would automatically notify any of the computed signals to update. And under the hood, it was relying on ticks, like JavaScript ticks, to evaluate changes. So between ticks, the values are mutable, and that provided for a consistent timeline. And so because it's through ticks, data changes could get batched into a single tick. And so, yeah, so it just kind of creates this scheduling to run it. But it also did automatic garbage collection of dependent computations by the parent signal. So the parent owns all of its children, all of its dependents to handle the garbage collection. But a fun fact is that it called its reactive primitive a signal, and that's the origin of the term signal in JavaScript. So by 2019, across the JavaScript ecosystem, we had all of the component parts of signal-based reactivity. Fine-grain reactivity, push-pull, all of that. Now, Solid.js was released in 2020, and Solid.js was really the first framework to combine all of these pieces into a single framework. This is a 100-second video that introduces Solid.js. It does a pretty good job of just sort of explaining the concepts under it. But what was happening in JavaScript was that the frameworks, all the JavaScript frameworks they exist in the same ecosystem, right? They all run on browsers. They all have the same problems that they're trying to solve. So they experienced a convergent evolution of signals because everyone was trying to solve the same problems at the same time. So this is another video link to Daniel Ehrenberg's talk about the signals TC39 standardization. This is a really great talk, and he goes really in depth about why it's needed and what they were thinking when they did it. I swear that link is there. But then we get the Angular Signals API. So what's special about the Angular Signals API, not just that I'm biased because I'm clearly an Angular dev, is that Angular collaborated with Wiz when it was developed. Now, I'm sure some of you are thinking, what is Wiz? Well, Google Wiz is actually the internal framework that's used by a lot of Google products. It's not a publicly available tool, and it's always server-side rendered, and it focuses on extreme code splitting and performance, but they had a need to have something like signals in Wiz at the same time that Angular recognized their need to have something like signals in Angular. Since they're both Google products, they collaborated. So if you've used any of these apps in the last couple years, you have used the Angular Signals API in your daily life. And in fact, the Angular Wiz Signals API is the basis for the TC39 proposal. Okay, so that was sort of the history. Now we're going to talk about what are signals. So signals hold state and notify consumers when the state changes. They're like little cells of data. So they are a first-class reactive data binding abstraction that do automatic dependency tracking. There's a one-way flow of data, and they also allow for lazy evaluation and memoization. They provide a tool for synchronization and to get us to that consistent and glitch-free propagation, right? We don't want to have to refresh things to get the right state. They also will display the accurate state at all times. So when you make a change in your cart, it's automatically going to be reflected in the DOM and the other places as well. This is improved reactivity performance. So we don't have to figure out how to chain together observables or anything like that. So signals enable push-pull, fine-grained reactivity. All right, so if we look again at the spreadsheet example, so they work very similar to spreadsheet formulas. A lot of us have written spreadsheet formulas at some time, maybe in college, maybe at a job, maybe just because you're a dork like me and you have a mortgage amortization table that calculates how much you still owe on your house. But there's two different kinds of signals, really. Like there's a couple of different kinds, but the basic pieces, we have writable signals. And now these are, like I said, across the JavaScript ecosystem, signals like concepts exist everywhere. They just might have different names. So if you're a Vue developer, you would call them refs. If you were working in Knockout or MobX, they would be called observable. In Angular, it's a signal, and so on. There's also the idea of computed signals. Now, these are signals that rely on the writable signals to handle calculations. And again, they exist across all the frameworks. They just might be called something different. So if we look at our example of our little spreadsheet, We've got our declared values. These are our writable signals, right? These are the values where we declare the number of guests, the cost per guest, employee discount, tax rate, right? These are the things that I might change. And then we have the properties that are dependent values. So these are the computed signals. These values change as those writable values change. Now, a computed can rely on any number of writable signals. It might rely on just one, it might be two. It can also rely on a combination of writable or computed signals, or it can rely on many computed signals, or totally just on computed signals. So under the hood, we've got our dependency graph, right? So the dependency graph is a directed acyclic graph, or a DAG. The edges between the vertices have a direction, right? So we can see here that we have a direction, but there are no cycles, there are no closed loops, right? So it's always kind of going like one way. All right, so when any value is read, any related calculations are executed. So again, the execution is deferred until the value is read. So when a signal gets a new value, the signal knows how to notify its consumers that, hey, I got a new value. But then the reactive system that those signals are part of will have to cause the signal value to be read again, which then re-triggers the execution. So there's kind of two parts of it. There's the dependency graph that's capable of saying, hey, I know I have a new value, but then there's the reactive system that that dependency graph is inside of that knows how to re-trigger the calculations to run again. So you have to keep signals inside the reactive context. This is probably the biggest mistake that I personally have made, and I've seen other developers made in Angular, where you read a value in a signal and you're not reading it in a reactive context, so it has no way to trigger re-execution. So you can read a signal anywhere, but you can only re-trigger execution if you read it in a reactive context, is basically what all these words say. So, okay. So if we go back to our spreadsheet example, so as our writable value changes, computed values are gonna update, right? So if I change the cost per guest, the calculated values are gonna change. So under the hood, there are some signals have component parts. There's a constructor. Angular uses factory functions, but it's kind of the same idea. There's some way to make a new one. There's getters. There's a way to get the value, to read the value. There's setters, a way to set the value. And then there's that consumer tracking layer under the hood. So the writable signal initialization, if you look at the TC39 proposal, that's here at the top. But then you can see, so if you've used Vue, if you've used Solid or Angular, there's a similar concept across all frameworks. It's just, again, the actual semantics change a little bit. Then there's computed signal initialization. One thing to note here is that they all take a callback, right? So computed functions have to know what to execute when their value gets changed. So like a writable signal, you might be changing the value directly, whereas with a computed signal, there's going to be a callback that gets executed to be able to find out what the new value is. So we have writable signal setters. So, in Vue, you're going to call .value. In React, you're going to call .set. You invoke the set method. In Vue or Preact, you're going to just set the value. And then there's getters, where you're either invoking .get, you're either reading the value, or in the case of Angular, Solid, and Knockout, you just invoke the signal itself. The signal is the getter. But they don't replace asynchronous code. So if you're an Angular, are there any Angular developers here? A couple, yeah, just a few, yay, me too. They don't replace asynchronous code. I think that was the biggest confusion for the Angular community when signals first came out. We're like, oh my gosh, did these replace observables? Like I literally just figured out RxJS. And they don't, because they handle different situations. Promises, observables, async await, they are asynchronous. They often handle every value. These are great for like HTTP requests. They can persist data. They can also retain previous states. So with an observable stream, I can use like the scan operator and actually keep track of my state within the observable itself. Whereas signals are synchronous. Once you create them, they exist. They might be undefined, but they're already there. They retain only the most recent value, and they may lose values because in order to execute them, they have to be scheduled to be executed. Right? So this means they're really only meant to contain the current state. So signals are going to be working in conjunction with asynchronous code to provide a reliable user experience. Now, there's obviously ways to only use signals, but you have to understand that sometimes asynchronous stuff happens, right? We make HTTP requests. We have timers that go off. We have page timeouts that happen. We have user clicks, right? Okay, so why do we want signals? Okay, so once again, if we do a vanilla implementation of our spreadsheet here, first, we're going to have to say, okay, we have some constant values, right? We know the cost per guest, guest count, employee discount, all that. And then we're going to have our calculated values, right? So I'm going to make a function that knows how to calculate the subtotal. I'm going to need that subtotal to calculate the total discount, and so on and so forth, right? This doesn't look too bad, right? But what happens when something changes, right? So how does our rendered view react to changes? So if I change something, I'm going to have to remember to invoke all of the functions again, right? So I'm going to have to create some sort of function that says, okay, if this changes, go ahead and rerun all these things, right? So if any value changes, like I said, we're going to have to rerun every single function to make sure that the results are consistent. And that starts to get really complicated. This is why we don't really often write vanilla JavaScript anymore, because it gets the mental load to do it all gets to be a lot. So signals have built-in dependency tracking to react to value changes. So when we're using vanilla JavaScript, it's going to require a lot of boilerplate just to set up and just a lot of code to maintain. You have to remember, oh, shoot, I forgot to recalculate the subtotal. That's why this isn't right, right? So signals have built-in scheduling to know when to evaluate dependencies for changes. And in vanilla JavaScript, we have to actually invoke it ourselves, right? We don't have like some sort of machine that's running. There's no change detection running. We just have to say, okay, when this happens, make sure and do all this other work. And we have to know what order to do it in, right? Like we can't do the subtotal before we do the employee discount. So reacting to changes is honestly the biggest reason that JavaScript frameworks exist, because that is the hardest thing to manage in vanilla JavaScript. So signals improve the developer experience by performing operations synchronously. Our brains work better synchronously. I don't set up some sort of like reactive system so that I know what to do when I get in the bathroom and I need to wash my hands, right? I'm like, I go to the sink, I turn on the sink, I get some soap, I wash my hands, you have a whole process, right? We tend to think procedurally about our lives. And since signals perform operations synchronously, we can procedurally call out what needs to happen. So signals internally manage their own dependency tracking, so I don't have to figure out like I need to also update the cart. I can't forget to invoke that one thing, right? And they handle their own garbage collection. So the Angular devs here know the pain of working with observables and leaving a subscription open and having memory leaks, which you notice like once your app gets to be gigantic and you have to go in and touch every single component to fix it. All right, so signals improve performance because all the consumers get the same value at the same time. We get glitch-free computations, so we don't have to like rerun it to make sure that it's right. And individual DOM nodes can be targeted for updates with fine-grained reactivity. So in Angular, since signals tell you when something changed, we know something changed. So in Angular, we use zone to detect changes. Zone doesn't know what changed. Zone just knows that something happened. It's like, hey guys, something happened. Better go run all your code and figure out what. Signals gets us a way to say, hey, node number 5 just changed. I need you to go update that. So we have the writable signals, we have computed signals, and then we also have signal effects. So not everything is going to fit into the writable signal or the computed signal. We need to have something that is triggered to run when things change. And so effects are what handles that. So writable signals, we declare a writable signal by invoking the constructor or the factory function. These examples are in Angular. If we want to change the value, we can call set. We can call an update method, which gives us access to that previous value. And then to read the value, we just invoke the signal. Computed signals declare the callback that should be run when the signal value changes. They are read-only. There is no way to directly update a pure computed signal. And to read the value, same thing, you just invoke the signal value. Now, effects are a little different. So you can declare a signal effect. Now, what'll happen is when this value changes, the effect will schedule itself to run the callback, right? So it's important to know that like people say, oh, it invokes like when the value changes, it'll invoke the effect again. It doesn't actually invoke it right then, it schedules it to be invoked. And so if you write code like this, where you do like a set timeout where you very rapidly change the value 3 times, the only value that's going to be console logged is that last value, because that's the only one that exists when it's actually executed. And so that's where we say that signals can possibly lose values. So why do we need standardization of signals in JavaScript? So the API of the TC39 proposal looks very much like existing signals implementations because most signals implementations are almost exactly the same. So there's a constructor, there's a getter, and there's a setter. That's the public API. That's what we care about as developers. The intention is not that signals are going to go in and make libraries change everything. They're meant to standardize the signal under the hood, and the library authors will then wrap that implementation. So as developers, as a Vue developer, you shouldn't expect to see changes to how Vue is written, other than what maybe Vue would be doing anyway. Same thing with Angular, or yeah, so. And so this means that the developers who use our libraries, we won't really see existing code changes, which is what I just said. All right, so why do we need that standardization, right? If we're all kind of similar already, like why do we need it? Well, it's convergent evolution or carcinization. So like all of these things are crabs, right? They're all crabs, but they're not all crabs. Some of them are crab-shaped. And that's because it turns out when you live on the bottom of the ocean floor, being crab-shaped is like advantageous. Having big claws to grab things and feet to walk around. And so that's how we end up with things that all look the same. So the problem with all these different implementations, these crabs and almost crabs, is that it makes it really difficult to do interoperability. It also makes it really difficult to improve performance and build dev tools. Like why would Chrome or any other browser take the time to develop a tool specifically just for one framework's implementation of signals? So the signals standardization for interoperability wants to decouple the reactive model from the rendering view, right? So instead of so the frameworks are gonna end up handling what gets rendered. So this will allow switching out non-UI code in different frameworks. And it allows signals to, the signals implementations in JavaScript libraries can work then between frameworks. If you're an Angular dev, you know that a lot of stuff doesn't work for us, and a lot of that reason for that is because of our zone dependency. But there's like, anytime there's any little differences that can make things not work so you can't share tooling between libraries. So in addition to the standardization, they want to improve developer tools, right? So improve support for inspecting signals to understand what's happening with your signals so when you have a problem, which makes for easier debugging, and to make enhanced memory profilers and performance tools in the browsers. Like there's some really cool performance tools already, but it would be great if they could hook into a more standardized version of signals. So the goals of signal standardization is to convert the core features already implemented in JavaScript frameworks, or to cover those, right? We don't want to leave out like, oh, oops, we forgot about the setters, right? They'll have all those like core pieces already built in, like the memoization, like dependency graph. This provides soundness by disallowing unsafe or risky operations. There's things you can do with signals that can cause problems. It provides an API service that can be used directly or implemented in frameworks. So if you're writing vanilla JavaScript, you can still use signals. But if you're writing a framework, you're just using what your version of signals, and you may not be aware that anything has changed under the hood. And it will also provide memory management options, so garbage collection. There is an early sketch. This is a link to it. There's a polyfill that you can add and test it out. And they actually need people to do that. And so from the TC39, this is a quote directly from it. So like literally what they want to do is not change every framework, but change what the frameworks sit on top of. So that instead of trying to make everybody write their code differently, they're just providing that standardization under the hood. The framework responsibilities are still going to manage effects or watchers, right? So if I write an effect in Angular, it's the Angular framework that handles when that's going to happen. It'll handle the ownership and disposal and schedule the rendering in the DOM. So it's not going to change how Angular re-rendering isn't going to be changed by the TC39 signals implementation. It may change because of signals, but it won't change because of the standardization. So I think I'm just saying the same thing over and over again here, but yeah. You know how when you get on a roll and you're making slides and you're like, yeah, oh yeah, and then you get up here and you're like, God, that says the exact same thing. All right, so I hope you're as excited as I am about it, and you're probably like, cool, when is this gonna happen? And now the uncool thing is that TC39 proposals take forever. We're still, last time I checked, we're still in stage 1. But there is significant enthusiasm across the JavaScript ecosystem. So I feel like it'll get better traction. Like it's technically there's an observable TC39 proposal as well that never really got traction. So I feel like it'll get more traction than that because the future is bright for signals in JavaScript. Now, if you want to be part of the signals story, you can do that by testing out the TC39 signals implementation. And again, there's a polyfill you can add and test it out. And it's great if people are able to do that because, you know, you really don't know if a tool is working until you try it out in a bunch of different situations. You can contribute directly to the TC39 signals API. They actively answer questions about it. You can also create content or documentation similar to what I've done here today. So I care about signals. I really like using them in Angular. I'd love to see them broadly, I mean, they are already broadly adopted across the ecosystem. Angular is really late to the game. So I stand up here like, oh, Angular is awesome with signals, but really like, you know, we're just kind of like showing up at the party at the last minute when it got cool. So, I mean, it was cool before we got there and then we showed up. So, but yeah, create documentation. And then again, thanks for coming. Now, one slide I don't have in here, and I'm gonna put on my people glasses so I can see you, because I can only see so far. Some of you are there any React devs out here? Yeah, you're probably thinking like, what about React? What about signals in React? It really doesn't, it's not a thing that exists in React. Because of the way that React does its change detection and its rendering. There really doesn't, I don't think there's been as big of a need for it. But that I don't know what that means for the future. So, but I think I can't do math. 30 minutes. I think we're out of time, actually. So we should all go over there and get our picture taken. But I did want to thank you very much for coming. If you have any questions, feel free to ask me. I'll mill about. But otherwise, yeah, thank you for attending. Thanks for coming to the conference. I hope you had a great time. Is anyone staying for NGConf the next couple days? All right, sweet. I'll see you there as well. And for the rest of you, safe travels. Did you have, we can do clapping. Yay, clap for me. It's the only reason I do this. All right.